guys, Physics in the Flesh is back with non-uniform circular motion. A car at a racetrack accelerates uniformly from the pit area, going from rest to 315 kilometers per hour in a semicircular arc with a radius of 215 meters. Determine the tangential and radial acceleration of the car when it is halfway through the turn, assuming constant tangential acceleration. If the curve were flat, what would the coefficient of static friction have to be between the tires and the road to provide this acceleration with no slipping or skidding? So first things first, let's draw our picture. We've got a car moving in a semicircular arc, so it's a pretty easy picture to draw, something like that. Okay, we know that at the beginning, the speed V0 is 0. The car's starting from rest. Okay, we know that after it reaches the other end of the semicircle, it's traveling 315 kilometers per hour. So V is 315 km per over H. Now, I already know that I have to convert that to meters per second, so I'm going to do that in just a sec. Radius of the arc, okay, that's 215 meters. R equals 215. And that's all the information we're given so far. Okay, so let's convert this over. So 315 kilometers per hour. Remember, this is how we convert. We multiply by 1 twice. So times 1 times 1. Replace those ones with empty brackets that have blank fractions inside of them. Okay, for the first one, get rid of kilometers, so put it on the bottom, meters on top, that's what you're trying to get. The ratio of meters to kilometers that gives you 1 is 1,000 meters is 1 kilometer. Do the same for hours. You're trying to get rid of it, put hours on top, put seconds on the bottom. What ratio of hours to seconds is equal to 1? 1 hour is 3,600 seconds. Okay, so thereby you effectively cancel out the kilometers, you cancel out the hours. So 315 kilometers per hour, multiply by 1,000, divide by 3,600, and you get V equals 87.5 meters per second. Okay, so 87.5 meters per second is our final speed. So, okay, a couple things I want to draw on the circle here. Okay, the question tells us that there is, well, we're going to assume constant tangential acceleration. And what makes this question different from the standard circular motion problems is that it's non-uniform. Okay, so with circular motion problems, we know we have centripetal acceleration. That's the acceleration that at any point is always pointing towards the center of the circle. There, there, and there. Any point you pick, acceleration, centripetal, always pointing towards the center. Okay, and that's because the speed going around this circle is constant. Okay, so let's say at this point it was 15 meters per second, then here it would be 15 meters per second. Here would also be 15 meters per second. But take a look. We were told that at the beginning of the arc, the car's going 0, and at the end it's going 315 or 87.5 meters per second. Therefore, it must have accelerated in this direction as well. Okay, so that means there has to be another component of the acceleration going like this, tangential to the circle. Hence, why we call it tangential acceleration. And that is perpendicular to your centripetal acceleration. Okay, so that's what makes this non-uniform. You're accelerating in two different directions. The inward one is simply there to change your direction. The outward one's actually increasing your speed as well. Okay, so constant tangential acceleration, let's find that first. Okay, so we know that our initial speed is 0 meters per second. We determined our final speed to be 87.5 meters per second. Okay, what distance is the car driving through in this pattern? Well, if this is half a circle, right? And we know that the distance for an entire circle is the circumference. Therefore, the distance here is going to be half the circumference of a circle. Okay, so half C of a circle. Now, the circumference of a circle is 2 pi r. Okay, so therefore, we're looking at half of 2 pi r. Okay, if you multiply 2 by r by half, the 2's cancel, leaving you with pi r. So delta D equals pi r. Our radius of the curve is 215 meters. So this just becomes 215 pi. So there's your delta D, there's your V initial. Okay, and we're looking for tangential acceleration. So we're going to go ahead and use the following kinematics formula. We're going to use 2 acceleration delta D equals v final squared minus v initial squared. Now taking that formula and rearranging for acceleration, divide both sides by 2 delta d. So at equals v squared minus v naught squared over 2 delta d. Okay, we know v naught is 0, so that's nice. That just disappears. So we're left with v squared over 2 delta d. Okay, so our v is 87.5 meters per second. Square that, divided by twice the distance. So twice of 215 pi. When you punch all that in your calculator, you're going to get that the tangential acceleration is 5.67 meters per second squared. And because we're told it's constant throughout, then determining the tangential and radial acceleration halfway through the curve, it's the same everywhere. Okay, so this is the acceleration tangential here, here, and here. Okay, so that's constant. So there's half our answer. Okay, now we have to do the same for centripetal acceleration, but be careful. Okay, we were told assuming constant tangential acceleration. That's okay. But centripetal acceleration, you got to be careful what speed you plug in, because remember, the speed is 0 here, 87.5 here. We're asked to find it at the halfway point right there. So the speed, okay, you cannot assume it's halfway between 0 and 87.5 because it's accelerating. Okay, so we have to first figure out what the speed is to plug it in the formula for AC, which is the v squared over r. Okay, so so let's do that next. Okay, so to get centripetal acceleration, we need the speed v at the halfway point. Okay, so let's do that. Now take a look at this picture. At the halfway point on this circle right there, that's a quarter of a circle, right? So the distance you've traveled is a quarter of a circle. Okay, so whatever you had here, 215 pi for the half circle, it's half of that again. Okay, or if you're doing it directly from the circumference formula, it's a quarter of the circumference. That's the distance you travel, and you're trying to find the final speed at that point. Okay, so we know that delta d, the new delta d that we're looking for, we'll call it delta d star, is 1/4 the circumference of a circle, which is 1/4 of 2 pi r. So what happens here, those cancel, you're left with a 2 in the denominator, so pi r over 2. Okay, pi r over 2, when you plug those values in, you're going to get that your delta d star is approximately 107.5 pi meters. Okay, so there's your distance. That's the quarter of the circle. Now, we have to figure out the speed at that point. Now, we know the acceleration, the tangential acceleration is this value. We know the initial speed. We know the distance it travels through. So we have to find the final speed. We're going to use the same formula, just solve it for something else. Okay, so here we go. 2a tangential delta d star is equal to v final squared minus v initial squared. I'm calling it v star for v final because it's a new speed. So on our picture, that would be right here, v star. Okay. Now, what else? We already know v naught 0, just like before, so that disappears. And we're looking for v star. We're already isolated for that, so bring that to the left. V star equals the square root of 2 times acceleration, 5.67 meters per second squared, times your delta d, 107.5 pi. Okay, punch those numbers in your calculator. You're going to end up with the square root of 3,829.76. And take the square root of that, you're going to end up with v naught, or v star, 61.89 meters per second. Okay, now that's the speed halfway through the circle. And that's the speed we're going to use in our centripetal acceleration calculation. Okay, so here we go. Centripetal acceleration halfway through the circle is v star squared over r. Okay, so v star is 61.89 meters per second squared divided by the radius, same radius, 215 meters. Plug that in and you're going to get centripetal acceleration is 17.8 meters per second squared. So there is your centripetal acceleration halfway through the curve and your tangential acceleration halfway through the curve, which in this case turns out to be the same everywhere and halfway. And centripetal, of course, we had to find the speed halfway, and then we could plug it in the formula to find the centripetal acceleration. So far so good. We are almost done. We've got about 20-25% of the problem left to do. The last part asks us, well, if the curve were flat, what would the coefficient of static friction have to be between the tires and the road to provide this acceleration with no slipping or skidding? Okay, now in previous problems, whenever we're talking about friction, coefficient of friction, we always dealt with centripetal acceleration. But here we have non-uniform circular motion. We have tangential and centripetal acceleration. So the acceleration that's contributing to static friction is the total acceleration. So we have to combine these two, which are currently at right angles, to find the total acceleration to see how it affects static friction. Okay, so that's going to be our first step here. So we've got tangential acceleration going in one direction. We've got centripetal perpendicular to it. And so the total is going to be the sum of those two vectors. I'll call it A subscript capital T for total. Those two are at right angles. Therefore, we can say that A total is equal to the square root of A centripetal squared plus A tangential squared. That's just Pythagorean theorem solved for the hypotenuse. Plug in your values, so AT is equal to the square root of 17.8 meters per second squared plus 5.67 meters per second squared. Oh, squared is the unit as well. And those values are also getting squared. And when you solve that and you take the square root, you're going to get 18.7 meters per second squared. So there's my total acceleration. Now, how did that help us? Well, we are looking for the coefficient of static friction between the tires and the road. Okay, so to look at the coefficient of static friction, we need to know about the force of friction. Okay, so this is the idea. You've got a car on the road, and regardless of how it's turning, let's say it looks something like this. Here are the tires. Assume this is this is definitely not a good picture. Assume that's the front of the car. There's your grille, your windshield. So let's look at the forces acting on it. You've got your force of gravity going down. You've got your normal force going up. And let's say the car is going around the circle. Honestly, it doesn't matter which way your static friction is pointing because we're not really concerned about that. Let static friction be going inwards like this, okay? So we know that the force of static friction, FFS, is equal to the coefficient of static friction times the normal force. And in this case, the normal force is equal in magnitude to the gravitational force. So that's equal to mu s mg. Okay, and that's because it's a flat surface. The force of static friction, in this case, it's the only centripetal force. It's the only net force in the horizontal direction. So FFS is equal to ma. And which A? It's the total A, not just centripetal, because there's another force and another acceleration going like this. Okay, there's an acceleration going tangential, there's an acceleration going centripetal, and we added those together to get the total. So make sure you use the total here. Okay, so this allows us to cancel the masses out, leaving us with mu s is equal to the ratio between the total acceleration and the acceleration due to gravity. Okay, so there we go. Plug in your values. 18.7 meters per second squared divided by 9.8 meters per second squared. It's beautiful. Your units cancel out. You're left with a unitless ratio, which is exactly what you want. And we need that to 3 sig figs, so 1.91 is our final answer. And there you have it. 1.91 is the coefficient of static friction. So guys, I hope that was helpful. Hopefully you saw the distinction between uniform and non-uniform circular motion. If you do still have questions, be sure to leave your question in the comments section below. And other than that, be sure to click that like button and subscribe to my channel so you never miss a video from me. See you guys tomorrow.